Here we're going to talk about the mean value theorem. This has a similar flavor to Rolle's theorem, and it's almost always proved by reducing it to Rolle's theorem. I'm not going to talk about the proof here, but I'm going to talk about the intuition and the careful statement. So I like to talk about our intern Scooter. Once again, he's traveling on I-25. I'm going to idealize that as north, just a straight north-south. But the main thing is that it's one-dimensional. There's no turns, turn-offs, there's no loops or anything like that. And he's going from Albuquerque to Santa Fe. He leaves Albuquerque at noon. And here's the thing. If you're not in my class, you don't realize this, but we've been worried about Scooter's habit of speeding, and he says he's sworn off that. But here's what happens. It turns out, let's say it's exactly 50 miles. Somewhat close. Let's say it's exactly 50 miles from, say, north side of Albuquerque to south side of Santa Fe. He calls us right as he's leaving the north side of Albuquerque at precisely noon. And then he makes the mistake of calling us right when he arrives at 12:30. Okay, and so we're thinking, wait a minute. Okay, we're going to take that 50 miles and we're going to divide that by 1/2 of an hour, or in other words, times 2. Whoa, 100 miles per hour. Speed limit's just 75. Seems like he's speeding. Okay. And so what's Scooter going to say to that? What's he going to try to? How's he going to try to get out of this one? And one thing he could say is that, look, when the cop stops you, they don't talk about overall average velocity, and that's what we've calculated here. I like to emphasize this as an overall velocity over a whole interval. It's also called an average velocity, but it's not like something plus something over 2. Later on, we discover why it really deserves that word average, but I like to call it overall velocity. In any case, if you graph, another way to think about it is graph S versus T. Here's Albuquerque, here's Santa Fe. The main thing is that this, again, is 50 miles. And let's say time 12, time 12.5. We have calculated, he's known to be at this point at this time and this point at this time. And so we've calculated this secant slope. And Scooter could say, look, I claim, that's a weird S, Scooter claims that the instantaneous velocity, v of t, or s prime of t, the tangent slope, was never that 100 miles per hour. That's what he wants to claim. He really wants to claim it was never even over 75. But let's say he's sort of picking at this difference between, look, you calculated the secant slope. You guys are taking calculus. I thought you knew that there was a distinction between that and the tangent slope. But let's look at what some plausible trajectories, some plausible graphs of S versus T. Maybe he, if he was going along a straight line, he was pegging it at 100. So he's totally lying then. He might have started out a little slower, so that the tangent slopes are lower than this slope of the secant line. Oh yeah, so I don't know if I said the word secant line, but this is a secant slope. I want to make sure it's written down. Okay, and that's a tangent slope. But suppose he started out slower. Well, he would have had to make up for it up here, and there's going to be some point maybe right in here where it doesn't look very parallel, sorry, but this is supposed to be parallel to this guy. Well, maybe he started out fast and then got slow. Well, then certainly there's still another point where it's parallel. And there's also some places where he's really fast. He's actually over 100. In both cases, he's over 100 for sometimes. The mean value theorem is going to focus in one version, and sort of the most popular version, on the idea that this statement in particular can't be true, that he must be lying. If it's wiggling, it kind of looks like it's going backwards there. But there's definitely going to be then multiple places where it's tangent. You could try it yourself. Just pick 2 dots and connect them with a straight line, and try to connect them without having some place where the tangent slope is equal to the overall secant slope between the starting and the ending dots. Well, you can actually fake it. You can, but you have to go outside the bounds of reasonability for Scooter. Here's some ways we could cheat. we could think back to the ways we could cheat IVT, for example. It's a very similar kind of story, very similar situation, except we're bringing tangent slopes and derivatives and things into it. But the kind of thinking we had for IVT is okay. If you want to go from here to here and never have exactly the same slope as this guy, what you could do is just teleport. The zero slope, bim, you teleported from Albuquerque to Santa Fe. You never actually were going 100 miles an hour. There was no time when you had any kind of non-zero velocity. Something is really weird happening here. It's not differentiable because it's not even continuous. But that's one way to cheat. Okay, so just disallow this. Let's say f must be continuous. And in Scooter's example, that totally makes sense. It just says you don't have a teleporting car, Scooter. We happen to know that they're impossible. So don't try to pretend that that's how you're getting out of this. Okay. If you did have a teleporting car, obviously you wouldn't need to speed. It would not be an issue. What's another way we could cheat? Certainly all the other kinds of discontinuities, infinite teleports, things like that, anything that violates IVT is going to be a way you could cheat this and have some situation where you never match, where your tangent slope never matches your secant slope. But more subtly, we could have something where he's going along at really, really low speed, and then if he just wants to make this statement true, I was never going exactly 100 miles an hour, he go along really, really low speed, or like zero speed, and then have a sharp corner, doing, and do super, super steep. And maybe he's going like 5 miles per hour here, and he's going like 2,000 miles per hour here. He would still be speeding for a little while, but if he just wants to be really picky and say, look, I never was actually going exactly 100 miles per hour, that would be true, as long as this is an actual honest-to-God sharp corner. Not something where it gradually turns from 5 miles an hour to 2,000 miles an hour. But of course we know that this is something we typically disallow as well, and this is very much like the situation for Rolle's theorem. In order to disallow those guys, we're going to say f must be differentiable. Now, to be technically correct, Scooter could cheat even if he teleported at exactly the very last second. So just like in, oh, not seeing that. Just like in, so here's teleporting at the very last second. Just like in IVT, we need to require the function is continuous on the entire interval, including the endpoints, so that we get the statement we want. Turns out that you can't actually cheat if you're going like 5 miles per hour, near, and then like suddenly, right at the end, you go infinite miles an hour. Doesn't make any sense, right? So in fact, you can have a little bit less of a hypothesis on this on where it's differentiable. It doesn't need to be differentiable right at the endpoints, which is nice because checking differentiability at endpoints is a little bit awkward. Okay, so I claim basically MVT says that unless you cheat in one of these ways, discontinuity or non-differentiability, then there's going to be some place where the tangent slope matches the secant slope. And in a later video, I'll talk about how this gets used. Just like in the Rolle's theorem video, I did a little bit of logical turnaround with that to see how it got used in an example. There's often some sort of logical consequences of that that are more commonly used. But let's actually just state MVT carefully, and that'll be the end of this video. It says if f is continuous on a closed interval and differentiable at every point, no cheating anywhere. If you allow even one cheat, you can't say this. Differentiable on the open interval. Okay. Then, very much like Rolle's and IVT, it's the same family of theorems. Then there is some C, and it's not going to tell you much, hardly anything, nothing basically, specific about where that is, such that the tangent slope matches that secant slope. And the secant slope, of course, is just a very explicit calculation. Turns out this is actually a really deep, profound theorem, and it's the key to carefully proving so many things in calculus, because it gives you a link between what the function can do. Here's something that equates something about the function values themselves and the derivative with no limits. Usually the f prime is a limit of this kind of thing, It says that there are some statements you can make that says once you've calculated this derivative, maybe using limits, maybe using rules of derivatives, that you can actually conclude things about actual function values, not just limits. And that turns out to be pretty profound. So in next video, we will do a concrete example.